Right, good morning. Any questions or comments? So I will start talking about one of the most, in my opinion, exciting and influential topics of this course, superconductors. But before superconductors, let me talk about conduction, normal conduction in metals, right? In metals, we have like this regular lattice of, if you want, ions, and there are like electrons going around. And the question is, how can electrons just go through like so many ions and still conduct electricity, right? Typically, the distance between two ions is like order of angstrom. In principle, if electrons were to bump into every single ion, there is no way they could conduct, right? And we know the answer to this, and I think the course 409 is built on that. And the answer is so-called Bloch waves. So exactly like X-rays, electrons are going through the crystal lattice because they are waves. And these Bloch waves have the structure psi n. Let me write it and explain. R is equal to U n k of R e to the I k dot R. So this means the wave function of electrons is almost like plane wave, but there is like a modulation. And this modulation, like this so-called Bloch functions, let me skip writing vectors, right? Again, we know which labels are vectors. These Bloch functions obey the periodicity of the lattice, U n k R plus A. So this n here is, so this n is so-called band index. Exactly like particle in a box, they are like energy levels, but each energy level disperses with k. And as a result, we have a bunch of bands. Each band is occupied or unoccupied, and each level can take like two electrons, because electrons are fermions. Okay, electrons are fermions. So each of these states can be occupied with Fermi-Dirac function, e to the beta e minus nu plus 1. In the Bose case, this was minus. In the fermionic case, it is plus. And here, the chemical potential mu is determined by total number of particles. So let me write. So first, we have exactly like what we had in the Bose case, which we studied this integral. So this object. And of course, here, okay, let me decorate. So this is E and K, the energy of the band N, and this K is, by the way, K. It's kind of like momentum, but not quite. This is, sometimes we call it lattice or quasi momentum. And it is defined within the Brillouin zone. So we sum over all energy states, so each one is occupied. So this is the occupation factor coming from statistics. And now we need to sum also over all bands, and also we need to put 2, because we are studying electrons. So this is for spin.
So it is 2 pi to the power of 3, right?
Oh yes, thank you, absolutely, yes. And typically what happens is we focus on highest band. Sometimes we call it conduction band, and we ignore the other bands because other bands are like deep in the energy level and they are occupied, they are intact. And within this one band model, what is important is typically there is like a region, KBT, is much smaller than chemical potential, and it's approximately so-called Fermi level. Let me also draw that. If this is occupation, this is energy, there is like a highest occupied energy, right? You start filling up available states from ground up, and at some point you run out of the electrons because you located everybody, so you just go down. So this is what we call Fermi level. So this is at t is equal to 0, and at finite t, this is exactly like the finite, but of course with this condition it just smears out, something like that. And the amount of this smearing, this is kT, or let me be careful, kBt. And the picture is something like this. So we have, so this, let me draw like a two-dimensional picture. We have this Fermi surface. Okay, this is ky, this is kx. So there is like this, I don't know, k Fermi. And there is like a thin shell around Fermi surface, and the width of this thin shell is kBt, and these are the guys who are contributing to conduction. So these are conduction electrons. Now let's try to describe this with so-called Drude model. So Drude model. So Drude model takes electrons like a classical particles and uses Newton's equation. F is equal to ma, and F in this case is there's like electric force minus E times E, and there's also like a direct force, and direct force is mv over tau, and here this tau is so-called scattering time, which is like a phenomenological constant. We don't know what it is, but we can extract it from the experiment. And in the steady state, like steady state, F is equal to 0, then E times E is equal to mv over tau, or V is equal to E tau divided by m times electric field. You can also put vectors, and the current is defined as minus, okay, there, I think I need to have like a minus here, minus E and V, which gives us E square and tau over m, E square and tau over m times E, and if this is vector, this is also vector, and the coefficient of this relation between J and E is going to give us so-called conductivity, and this is Drude conductivity. Sigma is equal to E squared and tau over m. And resistivity is inverse of conductivity. If you want, resistivity is defined by electric field is equal to rho times J, and from here, which gives rho is equal to 1 over sigma, and it's going to be m over E squared and tau. And the unit of resistivity here is like it could be like ohm times meter, but typically we use ohm times centimeter because that's more the experimental dimensions. Now, what is tau? Tau is defined by, like I said, scattering time, and there are basically three main scattering events in any solid. What are they? Let me ask if people know this. In a solid, what are the main things that prevent conduction? Lattice scattering. What do you mean lattice scattering? So the scattering from these ions. So interestingly, in the Bloch description, this is fully taken into account. And as long as you are in a bandwidth, there is no scattering from these, right? Electrons just go through like X-rays.
You just, I guess, put the potential, you take, you count it as a potential, right?
Yeah, you apply a potential and contribution of resistivity from these periodic ions is zero. There is no resist. There will be in a little bit, but there is like a different mechanism. Anybody else? What is that? Phonons. There is like phonons. If these guys are stationary, they don't contribute. But if they are like vibrating, we know these are quantum objects, and they are like phonons. And one of them is, let me write phonons. Phonon, electron scattering. I think at some point I want to introduce phonons and I want to quantize and show you how to do this, but we don't need it at the moment. What else? Exactly, there is electron-electron interaction. So this is the most complicated thing, and it is very technical. We may or may not talk about it. And there's one more, and this is the most, from like a practical point of view, the most important one.
Nuclei.
What's that? Nuclei, like impurities, right? Like you can have this periodic lattice, and every once in a while you may have like a lattice vacancy, or maybe there's like a foreign atom, or maybe there's like some line dislocation. There could be all kind of impurities, and we package them in the name impurity scattering. And this is the most important one because typically solid materials, they'll always be impure. You can never have like 100% pure substance. And the name of the game is like how to make them purer and purer and purer, because typically you don't want them, right? In the semiconductor industry, the whole idea is how to just eliminate these unwanted objects. So then the scattering time, tau to the minus 1, is going to be tau to the minus 1 impurity scattering plus tau to the minus 1 electron-electron interaction plus tau to the minus 1 electron-phonon interaction. And this is so-called Mathiesen rule. This is an approximation, but empirically this is very, very good. Like if you look at the results from experiments, somehow this works. And this is temperature independent. This one is, I think we'll come to this at some point, but this is like T squared. There is like a phase space argument why two electrons needs to have T squared dependence, and this one is T to the 5 dependent. That means at low T, at low temperature, which is the main interest of this course, the resistivity is going to be some constant. This is the lowest order contribution coming from impurity plus some which coefficient, A times T squared, and higher order terms. So this one is what we call residual resistivity. Good. And probably many people wanted to test this, but one of the famous people who wanted to test this result was Kamerlingh-Onnes. And what he found was, okay, let me draw. So this is rho, this is T, and what he found was like there is like some saturation level, and as this suggests, there was like some parabolic approach, but what he found was at some critical temperature this thing just jumped, and here he found zero resistivity or zero resistance, and this is TC. And this is typically the case for many many materials. There are like some like small technical details, but typically if you take a piece of substance, even if they are not metals, if you take a piece of substance and cool it down to like Kelvin, sometimes microkelvin temperatures, typically we see this, right? It doesn't matter. And in Kamerlingh Ons, so this is Kamerlingh Ons, he did this with other substances, but like the one that's like cleanest, the one that gave the cleanest result was mercury, and he found this at Tc about, I think, 4 Kelvin. And this was the first experimental observation of superconductivity. And I think this is like 1911. So this is before any quantum theory, before even the name condensed matter or like solid state was not around, right? One of the most important effects in entire physics was discovered before there was like any trace of theory. But today we know like there are like many superconductors. So there are many others. Let me just write a couple of them to give you a sense of the diversity of this field. So let me start with like some elemental superconductors. I think this is niobium is like 9.2 Kelvin. If you take aluminum, it's going to be 1.2 Kelvin. So these are critical temperatures. Take a piece of this material and cool it down to here, you are going to see this behavior. Like tin is like 3.7 Kelvin. Lead, I think it's like 7.2 Kelvin. So interestingly a note, the best metals we have are like copper, silver, gold. They still do not have a superconducting phase. They are not observed. And many people believe that if you make them clean enough and if you go to cold enough temperature, you will see it one way or another. And a result that supports this argument is like platinum. Actually, in nanoparticles, has been shown to be superconductor. I think I didn't write the temperature, but this was actually observed nanoparticles in 1998. So another class is like sulfur, oxygen, and iron. If you go to high pressure, you make them superconductors. There are so-called A15 materials. So for example, one is niobium 3, germanium, this is like 23 Kelvin. And another one is niobium 3, selenium is, I think, this is at 18 Kelvin. And these two materials are very important because these are robust, very robust superconductors. As far as I know, if you have ever taken like MRI, for example, that technology is thanks to existence of these materials. LHC, for example, is thanks to these materials. If you don't have these materials, you don't have LHC. You don't have colliders, you don't have nothing. Like quantum computers are thanks to these materials. If you don't have superconductors, you don't have any of this technology. You have no chance. And there is no competitor either. Right? There is nothing else. I mean, there are theoretical proposals, but there is nothing you can do in the lab. And one of the most influential class of superconductors came in 1986 by Bednorz and Müller, so-called copper oxides. These are like high Tc materials. And it initially, the first one seen was at 38 Kelvin. You can see it is higher than these, but not terribly higher. But at the time, people were really excited because it was a completely different class of materials. These are not even conductors. These are like ceramics, and they just cool it, and they became superconductors, and people were very excited. Later, by studying like related materials, people went all the way up to 165 Kelvin. I think this is also one of the fastest Nobel Prizes. They wrote the paper in 1986. I think within less than a year, they got the Nobel Prize. Let me write others. They are like organic superconductors. So these are like polymers, like chemists, they know very well how to produce them. You take a piece of plastic almost, you cool it down, and they are superconductors. And so-called buckyball C60, I think this is called fullerene. This is also a superconductor, so-called, they are like a class of materials called heavy fermions. They are based on uranium or cesium. They are also superconductors, and they are also more recent. I think this came in like 2008, iron-based superconductors. So iron is a magnetic material, and it was actually like very surprising that, because we'll come to in a little bit, magnetism and superconductivity, they don't want to coexist, right? They don't like each other, but iron-based superconductor was like surprising from that point of view. Now I want to talk about zero resistivity. How come we have like a zero resistance in a piece of material? So we have rho is equal to 0. In that case, electric field is equal to rho times J. That means if rho is equal to 0, E is equal to 0 in a superconductor. So this is inside superconductor. But J doesn't have to be 0, right? There can be a finite J without an electric field. And this phase diagram we have started with. So this is rho, this is T. You just come down. There's like a critical T. So there's TC. So this is like a thermodynamic phase transition, and the phase here we call it superconductor. And here we call it normal metal. Sometimes we call it just normal and superconductor. And they are separated by like a TC. And the question is, how come we get rho is equal to 0? Right? How can you like 0 doesn't exist, right? How can you show a 0, right? Is it like 0.0001 ohm centimeter? How can I say, right? Is it like maybe a little bit resistance? It's like a noise here, right? But we know it is exactly 0, and I want to give you an argument for that. And the argument goes like, let's consider like a loop of conductor, and let's imagine like this is loop of conductor, and let's imagine we bring like a magnet here, and we pierce this through with like a flux. So there's like some flux. So this is magnetic flux. And we know what magnetic flux is. This is equal to B dot ds inside the sample. And we know Maxwell equation. So let's use Maxwell. Del cross E is equal to minus del B del T. So if you take the derivative here, what we are going to have is d phi dt is equal to dB dt dot ds. Let me also put like a minus sign here and a minus sign here. And this minus dB dt is curl of E. So let's write that. This is curl E. And now I can use Stokes theorem, right? Let's take this loop to be inside the conductor. Like I'm taking, so this area integral can be converted to loop integral, and the loop is going through the conductor, this loop conductor. So this is going to be E dot dr. So this is inside the conductor. But we said E inside the superconductor is 0. That's the, not almost, but not 100%, but almost the defining property. We'll see what is the 100% defining property of superconductors in a little bit. Then this is equal to 0. That means change in flux is 0. That means flux is constant in superconducting phase. And the way we do show this zero resistance is like we start with a B, start with like a flux, but above T is equal to greater than Tc, and lower the temperature and go to superconducting phase, T less than Tc, so this is superconducting phase. And now turn off B, right? Set B is equal to 0. And we know that the flux needs to be constant, right? Because that's what we showed. If you turn off B, superconductor should generate its own B so that it can maintain the flux. But phi is constant. Therefore, superconductor should generate a constant current here. So there has to be like a current going on so that flux is constant, and we still have this equation obeyed. And this is what we call persistent current. Right? After you turn off the external magnetic field, you can always go and look at the flux, right? Measuring the magnetic flux is the easiest thing in an experiment. And by measuring change in the flux, you can tell about change in currents. And typically, in the experiments, the lifetime of phi or lifetime of current is about years, right? You just generate this current and you just leave it be, and for years and years the current just keeps flowing, and that's how we know rho is equal to 0, because even if you have like tiniest rho, it should have like a dissipation and the current should decrease, which should decrease the flux. Good. Yeah.
I can ask what if it's just very small and it takes a very long time to dissipate?
It is actually a very long time, but like in some superconductors, the long time is age of universe. they calculate. It is not 100% constant. I think in some labs, I don't know, maybe they let it run for weeks and they find very tiny change, but if you extrapolate, you find like a very long lifetime. Of course, experimentally, nothing is zero, right? There is always something, but as far as measurability concerned, this is like zero resistance. So this is not the defining property of superconductors, like I said. The defining property of superconductor is so-called Meissner effect. And let's talk about that. So let's consider two different experiments. I have case one. Suppose I have like a piece of material, and I start with T bigger than Tc, and B is equal to 0, and then I cool it, and I go to superconducting phase, T less than Tc, and B is still 0, and then I switch turn on B, I switch B. In that case, what we found is the flux, right, in a superconductor needs to be constant. And since we started with zero flux, when you turn on B, this should be expelled from the superconductor. So what you need to have is like something like that. So this B you turned on cannot enter the superconductor. So this is because, so del phi del T is 0. That means del B del T is 0. That means B is constant. Because, and all of this follows from rho is equal to 0, like we just showed a minute ago.
The inside.
Because inside the superconducting phase, right, flux cannot change.
But we can say that there is a generated another P, so it makes the total B equal to 0, so the flux doesn't change.
But there is no B inside, right? Inside, how can you generate anything? So inside, anywhere in the sample should have 0 B. So that's what we found. If there is like 0 B, there is 0 B. Right? That's what we said. Like flux is a consequence of rho is equal to 0. Flux should be constant. And when you go to superconducting phase and turn on these blue lines, even if the blue lines are directed through the sample, they have to go out of the sample at the end. Good. But this is not Meissner effect. Meissner effect is actually stronger than that. And let's consider case 2 to see the Meissner effect. So let's start with this experiment. But let's turn on magnetic field. So this is, then we start with normal phase, but we turn on magnetic field, and then we just go to superconducting phase. So we just cool, and T less than Tc. But the Meissner effect, so this is, we are talking about phenomenology, observation, right? So we are not explaining anything at the moment. And the observation says, even in this case, flux goes outside. Okay, so this experiment cannot be explained. So this cannot be explained by rho is equal to 0. We'll see hopefully in the second hour or like next time. We have to think much harder to explain this. And this is what we call Meissner Ochsenfeld effect.
Is this initial field constant?
Initially it is constant, yes. There's like you bring the magnet, and what you do is you only lower the temperature. And as you go to lower temperature and enter the superconducting phase, the system, right? What we found earlier was B was constant. But this says B is actually 0, right? So this doesn't say B is constant. So in that sense, this is a stronger result than the previous one. And this happened to be a defining property. And we'll see why. Defining property of superconductors. And today, like there are like many experimental groups that get in trouble because they claim like superconducting phase, but there are like some complicated experiments, right? You cannot always go and measure magnetic field or flux. For example, these high pressure experiments, they take sulfur and hydrogen, those systems, and they crash it in diamond anvils, right? How can you go and put like a probe in a diamond anvil? The anvil itself is like a tiny system. Your entire superconductor is like, I don't know, millimeter size in like, I don't know, at maybe 10,000 times the atmospheric pressure. And now you are required to go and put some probe so that you can look at the absence of magnetic field. And you cannot do that. And then they first, like there are many nature science papers, they had to be retracted, which turned out their like Meissner experiments were not reliable. So this is a tricky thing, and that's a mandatory thing. In that case, Meissner effect is equivalent to superconducting phase.
Okay.
Uh-huh.
Are there any material that's not superconductor but result in case one?
Yeah, this is actually curious case, and the book says like there are some fractional quantum Hall systems. They have, so the case one is actually perfect metal, right? If you have like a perfect metal means rho is equal to 0, and it doesn't have to be superconductor, and you still have case one. And as far as I know, this is like this case one being a possibility in like some fractional quantum Hall systems is theoretical proposal. I don't know if it is experimentally verified. But it's like a tricky thing, like tricky thing to look for. Yes?
If we combine case 1 and case 2, I feel like there is some kind of a uniqueness in the magnetic vector potential.
There is some kind of?
A uniqueness.
Uh-huh.
We can find some kind of uniqueness in the vector potential. So does that mean that we need to just reject the gauge invariance or something?
So yeah, yes, we'll come to that. There is like a gauge invariance, right? How can you? This is also a tricky question, right? Sometimes people say that gauge symmetry is broken in superconductor. So it is tricky. We have to be careful with that. But what you call uniqueness is like whether you go to superconducting phase through here or through there doesn't matter, right? The history of system does not matter. And this has something to do with like thermodynamic laws. Thermodynamically, this means it's an equilibrium phase of matter, because it's not like hysteresis, right? Hysteresis, whether you go in one path or other, it depends. But if you always end up in the same system, no matter how you change experimental conditions, that means you are in a thermodynamic equilibrium. And this thermodynamic equilibrium phase is a new phase of matter. And we'll see that this will be the key for us to theorize superconducting phase. But gauge invariance, we'll come to that. It'll take some working out. Maybe in the second hour we'll see first traces of gauge invariance in the second hour. So let me also introduce something called okay, I have just a little bit of material. Let me give you the result, and then after that we can take a break. There's also something called, so we considered like perfect metal, and we now know perfect metal is not equivalent to perfect metal is not equivalent to superconductor. We can also introduce something called perfect diamagnet. So as we have gone through, like so we have some superconducting sample if you want, and so you apply some external, if you want, external field. We typically show it with H. I think the books, some books are calling it H fields, and this H field is going to give like an M field inside the superconductor, right? So this is M field, and so-called B field, the magnetic, sometimes people call it magnetic flux or magnetic flux density. Whichever way you use it, doesn't matter, but B is going to be equal to nu zero external H, the H field, plus internal M field. But we are saying that B is equal to 0 inside the superconductor, right? That's what the argument was. And superconductor is generating its M such that it cancels H. That means M is equal to minus H. And there is something called magnetic susceptibility. Chi is defined as dm dH as H goes to 0. That means how much magnetization you have given the external field. And from here we can see this is equal to -1. Typically, if this chi, magnetic susceptibility, if it's positive, we call it paramagnet. If it's negative, that means it is canceling the outside effect. We call it diamagnet. And it turns out superconductor is perfect diamagnet. Good. And if you look at the experiment, it is something like that. Typically, so this is chi, this is T. Suppose this is the 0 line, and suppose I have like this is -1. In the normal phase, you can have like some positive. Typically, many materials are paramagnet. There are also diamagnetic materials, but generally they are paramagnet. And if you go to superconducting phase, you are going to this diamagnetic phase. And this is TC. And let me introduce one last thing, and then I will finish it. From here, we have two kinds of superconductors. Two kinds of superconductors. There is so-called type 1, and type 1 is something like that. So you have external fields, and you have, let me write -m here. And in the superconducting phase, you have this M and H are linearly proportional, right? Let me try to make sure because susceptibility is supposed to be -1. But if you keep increasing the magnetic field, at some point you destroy the superconducting phase. And this is what we call HC, and this HC is generally temperature dependent. Whereas type 2 is very similar. You have exactly, let me erase that. So you increase until HC1. So this is HC1. And after HC1, you start decreasing, but you still have a superconducting phase. Like it is like something like that. And if you keep increasing, and typically this HC2 is much, much larger than HC1, it can be order of Tesla. So this is HC2 of T. After that, you have normal phase. So here, superconductor, here is normal. Here you have superconductor. Here, what we call Abrikosov vortex phase. And here we have normal phase. Another way to write the phase diagram is something like that. So here is first, here is the second one. So this one is critical field. This one is temperature. Here there is like TC, and as you go to lower and lower so this is HC versus T, yes. So this is HC is changing like this with critical temperature. Here is superconductor. Let me write it SC. Here is normal. Whereas in the, so this is type 1. Whereas in the other one, you have this TC. And you have one phase. This is HC1. You have the second phase. This is HC2. So this is what sometimes we call this Meissner phase, because in the Meissner phase, no magnetic field is allowed in the superconductor. This is Abrikosov vortex phase. In this phase, superconducting material accepts the magnetic field, but in the form of isolated vortices. And at very large magnetic field, these isolated vortices form like a crystal. And this crystal is called Abrikosov lattice. And let me write one more thing for you to compare with helium. So each vortex has a flux given by h over 2e. We are going to see why it is 2 and why it is not h over e. And if we have NV vortices, we have h over 2e times NV is equal to B times area of the sample. And from here, we have NV over A, which is density of superconducting flux, is going to be equal to B times 2E over H. And if you remember, you can compare this with helium-4. And in the helium-4 case, we had rotation vortices from the rotation, and we found so-called Feynman relation to M omega over H. Right? The role of magnetic field is taken by the rotation in the superfluid helium, but otherwise the physics is exactly the same. So B is identified with omega in superconductor. Good? Any questions? Okay, let's take a break and continue in the second hour.